All right, so we're going to start off with a little activity here. What I'd like you to do is graph each pair of functions. Now, you can do that by hand with graphing paper, or you can just use your GDC. Might as well do that since it's faster. Now, you should be able to graph these by, by hand. If you can't do them by hand, then that's something that needs some work. But pause the video here, graph each one, and see if you can see what sort of relationship you have, or see if you can see what's going on. Pause now. Okay, so I'll start with the first one. I have y equals negative 4x and y equals negative 1/4 x. Move over to the GDC. There they are. And when I hit graph, there they are. Okay. Maybe it's not so obvious what's going on just yet. Let me try another one. So now I'll do y equals 1/2 x and y equals 2x. Notice a quick tip here. If you click enter while you're on the equal signs, you can turn on or off each equation. So when the equal sign is black, like they are here, these ones will graph. So y3 and y4 will graph. And I turned off y1 and y2. So here we go. What do we get? Okay. So I can start to see something that might be going on. What have you got? I'll do the last one here. Maybe that'll make it more clear. So now I have y equals 2x minus 1, and I have y equals x plus 1 over 2. Let's see what this gives us. If I graph these, I get that. Well, let's look at each pair all together and see if we could figure out what's going on. I'm going to turn them all back on. So I have the first pair is on, the second pair is on, and the third pair is on. Remember, blue and red go together, police car. Black and pink go together, and then green and yellow go together. Can you see it? Okay, let's graph one final one, y equals x. Let's see if you can see it now. So what's going on graphically is that each pair is one graph flipped over the line y equals x gives the other one. So for example, the blue line flipped over this brown line gives you this red line. Okay? The black and the pink were paired. The black line flipped over this brown line gives the pink line. And the yellow line flipped over the brown line gives the green line. Okay? So each pair, maybe I'll turn some of them off so we can see it more clearly. Each pair is two that are the same as each other if flipped over the line y equals x. Maybe you could see it better with that pink and black pair, right? So if you flip the black one over the line, the brown line, you get the pink one. If you flip the pink one over the brown line, you get the black one. Well, do you know what this means? It means that they're inverses of each other. So now let's come back to our pairs of functions and pick any one, the first pair, the second pair, the third pair. And what I want you to do is label one F and one G. It really doesn't matter which is which. I'll take the middle pair here. So I'm going to take y equals 1/2 x and y equals 2x. And I'm going to name one F. So I'm going to say f of x is 1/2 x. And g of x is 2x. All right? And then maybe you picked the third pair or the first pair, it doesn't matter, but you label one F and one G. And now what I want you to do is I want you to compute a few things. F of G of 1, whoops, or remember this is equivalent to F of G of 1. So compute that for your particular example. Also compute g of f of 1, which is the same as g of f of 1. Okay. Then I want you to compute f of g of x. And then I want you to compute g of f of x. Okay, pause the video. Do those calculations. If you want to check your answers, do the one that I have. If you want to try another one, go ahead and do another one. Okay, so f of g of 1. Well, g of 1 means I put 1 everywhere I see an x, so that's going to be here. So g of 1, I can compute it on the side, is 2 times 1. It's 2. So this whole thing here becomes a 2. Then I have f of 2. I take the 2 and I substitute it everywhere that I see an x in my f function. So I'm going to get 1/2 times 2. 1/2 times 2. 1/2 times 2, that is 1. Okay, now I'm going to try it with g of f of 1. F of 1 means everywhere I see an x in my f function, I put a 1. So I'm going to have f of 1 is 1/2 times 1. That's a half. So this becomes a half. G of a half, well, I see my x here. So everywhere I see an x in g, I put 1/2. So I'm going to have 2 times a half. 2 times a half, what do I get? 1. Interesting. Well, now let's do f of g of x. See what that is. F of g of x, of course, I can also write it this way. G of x is 2x. So this is the same as f of 2x. I'll move this one down in a minute. So this is f of 2x. F of 2x means everywhere that we see an x in the f function, I'm going to put a 2x. So I'm going to have 1/2 times 2x. Well, 1/2 times 2x is x. Right? And if you want to see this broken down, I can do that very quickly. This is order of operations says we're going 2 times x first. But 2 times x times a half is the same as a half times 2 times x. You can multiply in any order. So I'm going to multiply in this order, and I'm going to choose to make my 2 a 2 over 1, because then I get 2 over 2 times x, and 2 over 2 is 1 times x, and 1x is x. Okay, so that's just a little bit of quick review. Okay, so f of g of x is x. Now let me do g of f of x. G of f of x, well, f of x is 1/2 x. So this here is 1/2 x. So I need g of 1/2 x. But g of 1/2 x, g, the function g says wherever I see an x, I have to put whatever my argument is. So I'm going to have 2 times my argument. My argument in this case is a 1/2 x. So I'm going to have 2 times 1/2 x, which is x. Interesting. So what we showed here is that with this particular example, f of g of x equals g of f of x because they're both x. Okay, f of g of x equals g of f of x equals x. And we showed this independent of whatever the value of x happens to be. So in fact, we showed that this is true for all x's that are real numbers. Okay, now this for all notation is beyond IBSL, so you don't need it. You could just say right here, x is a real number. X is in the real numbers, but I like it. It's a little more advanced. I don't think it's actually that sophisticated or that complicated. It's just saying that this is true for all x's that are real numbers. So if x is a real number, this is true. That's what that upside down A is saying. But optional for IBSL. Now, why do we have this relationship? We have this relationship because right off the bat, I chose pairs of functions that are inverses of each other. Okay, if you have a pair of functions that are inverses, then as a consequence, this will always be true. So let's get a few notes just on inverses then. The inverse of a function f of x is the function, some other function, that returns every output from f back to its input. If we can find a function that returns every single output of f back to its input, then that's called an inverse function. By the way, we have inverse operations because those operations get us back to where we started. So for example, multiplication and division are inverse operations because if we start with, say, 30 and divide by 6, we get to 5. But then, so this is like our output. But then if we take our output, start with 5, and multiply by 6, we get back to 30. Okay, so inverse operations are very similar to inverse functions. In fact, every inverse operation, if you wanted to, you could turn into a function, but that's another kind of discussion. Now we name such a function f inverse of x. And this little exponent of -1, it's not really an exponent. We say the word inverse, it means that we have the inverse function to the function f. And if we had a function g and then we had a function that takes all the outputs of g and puts them back to the inputs, we would call that function g inverse. If we had a function h that had a whole bunch of inputs and maps them all to a whole bunch of outputs in the range, and then we found another function that went back the other way and took all the outputs and put them back on the exact same inputs, we would call that h inverse. If we had a function sine that takes a whole bunch of inputs, maybe their degrees, 0, 1, 2, 3, and so on, and maps each one to some output, maybe their ratios of opposite over hypotenuse. And then we found some other function that could take every single one of these ratios and map it back to the exact same input, we would call that function sine inverse. An inverse function is the function that maps the outputs back to the inputs that they came from. Now, for a function to have an inverse, for that inverse to even exist, the function must be one-to-one. What does that mean? Well, I'll show you. First of all, every input of the function maps to one output. In other words, it passes the vertical line test, and therefore, it's a function. If every input maps to one output, not two or more, then it passes the vertical line test and it's a function. Additionally, every output has to map to one input. In other words, it passes the horizontal line test, not the vertical line test this time, the horizontal line test. And if it passes the horizontal line test, well, that shows that the inverse will be a function. So this is what it means for a function to be one-to-one. You can look at this and say one-to-one is basically talking about this one and this one, if you like. One-to-one means every input maps to one output, and so it passes the vertical line test, and it is a function. This is our first function, say f. And every output of f maps to one input. That is, it passes the horizontal line test, and so therefore the inverse, f inverse, is a function. Those are the conditions we need to have in order for this original f to have an inverse. So, if f and g, two functions, are inverses of each other, well, first of all, if they're inverses, we would normally rename g to call it f inverse. But for now, we're just saying hypothetically we have two functions f and g. We don't know if they're inverses or not. But if they are, then this implies that f of g of x and g of f of x are the same thing, and in particular what they are is they both evaluate to x, like we had in our activity at the beginning. And not only do they equal x for just one or two values of x, they equal x for all the values of x that are relevant. So usually all real numbers. Moreover, if you have two functions, f and g, and f of g of x equals g of f of x equals x, if they both equal x for all x, then the opposite direction is also true. Then you can conclude that f of x and g of x are inverses. This is sometimes called if and only if. And all that means is if you have the first side, then the second side automatically follows. And additionally, if you have the second side, then the first side automatically follows. Okay? It says you go both ways. If you can prove one, then the other one automatically follows, no matter which direction you're going. Okay, so this is all well and good, but it's a little bit theoretical. Let's get to something a little bit more practical. How do we find the inverse? Well, to determine the inverse of f of x algebraically, you're going to take y equals f of x. You're going to, well, that should say replace all x's with y's, and replace the y with an x, and then solve for y. Let's look at an example. Okay, so I've taken an example right from the activity at the beginning. F of x equals 2x minus 1. I want to find the inverse. So what do? Well, I take y equals f of x. In this case, f of x is 2x minus 1. So I have y equals 2x minus 1. I replace all x's with y's. Now in this case, there's only one x to replace with a y. But if there were more than one, I would replace them all. You'll see that in chapter 4. I also replace the y with an x. Then I solve for y. Add 1 to both sides. Divide both sides by 2. And now, what y equals is my f inverse. So I would say f inverse of x equals x plus 1 over 2. Okay, let's double check that we got it right. We can prove that these are inverses by showing that f of f inverse of x equals f inverse of f of x equals x. So I'll do that very quickly. F of f inverse of x, well, f inverse of x is this here. So I'll put this inside f of x. F of x says 2 times the input. This is going to be my input. So 2 times f inverse of x, which is, well, don't freeze. There we are, which is x plus 1 over 2 minus 1. Minus 1. This is x plus 1 minus 1. This is x. Good, that's what I wanted. So that's the first part. Now I need to show that f inverse of f of x also equals x. F inverse of f of x equals f inverse of, what is f of x? Well, it's 2x minus 1. And f inverse is x plus 1 over 2. So I'm going to have to put my argument right there. Add 1 to it and divide by 2. So I take my argument, 2x minus 1, add 1 to it and divide by 2. That works out to 2x over 2. That is also x. So we've just verified that yes, in fact, switching the x's and the y's, as we often say, or replacing all x's with y's and replacing the y with an x and solving for y does in fact give us the inverse. Great. All right, well, what about graphically? Well, to determine the inverse of f of x graphically, we're going to reflect the function, the graph of the function y equals f of x over the line y equals x. And we saw that right off the top. So if we had, for example, y equals f of x looks like, well, let's get a different kind of curve. This, if that's my y equals f of x, then what would the graph, should be careful here, that's not quite a function. I want to pass the vertical line test. Let's do that. Well, see, look, this is a vertical line. Bad on me. Okay, let's not get too excited here. Let's just go like that. Okay, so here, if this is my y equals f of x, then to get the inverse function, I need to reflect this over the line y equals x. There's the line y equals x. And I have to reflect it. Well, now this point is on that line, so it's not going to move. This point here it will come across to about there. This point 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 will come across to about there. Okay. This point will come across to about there. This point to about there. Whoa, something like that. This point will come across to about there. And so on, something like that. It should be a mirror image. And notice what's happened as well. If this point is, let's say, 5, 0, where did it go? It went, well, I didn't quite line this up right. It should come right about here to 0, 5. This point here, 0, -1, where did it go? Well, it came to switch the x and the y's. It came to here, -1, 0. In fact, every point on my y equals f of x, any arbitrary point, let's say a, b, if that point is on the light blue graph, then on the purple inverse, I'm going to get b, a. They're going to switch. So in summary, we really have these three properties, if you will, that algebraically we can find the inverse by so-called switching x and y and solving for y. Geometrically or graphically, we can find the inverse by reflecting y equals f of x over the line y equals x. And in terms of points, coordinate points, we know that if a, b is on y equals f of x, then b, a is on y equals f inverse of x. And that's a very important property that can be very useful. Now here's a question for you. Does f of x equals x squared plus 1 have an inverse? This is a quadratic. We know what it looks like. It's our parent curve quadratic shifted up by 1. Does it have an inverse? Well, in other words, is it 1-to-1? Because if it's 1-to-1, then it has an inverse. But if it's not 1-to-1, it does not have an inverse. And the answer is no, it's not 1-to-1. Even though it is itself a function, because it passes the vertical line test, it fails the horizontal line test horribly. It fails it here, it fails it here, it only has to fail in one spot, but I'm just pointing it out. It fails all over the place. And so, no, it does not have an inverse. And the reason is, because it fails the horizontal line test, if we were to come up with some sort of inverse, that inverse would not be a function, right? Think, when we reflect this over the line y equals x, what would it look like? Well, it would look something like this. This purple curve is the reflection of the original blue one, isn't it? But this purple curve fails very badly the vertical line test. Why? Because the original failed the horizontal line test. You can see these horizontal lines actually match up perfectly with the orange vertical lines. The horizontal line test is a test of whether or not a so-called inverse would be a function. So no, it doesn't have a functional inverse. Now, it actually has a relational inverse, but that's another story for another day. As far as we're concerned, no, it does not have an inverse. Here's another question. Is f of x equals the square root of x plus 2 minus 3 1 to 1? In other words, does it have an inverse? And if so, find the inverse. Well, I need some sort of idea what this looks like. Now, if I don't know what this looks like, I can use my GDC. So maybe let's do it that way for right now. Okay, so here I have y equals the square root of x plus 2 minus 3. I'm going to graph it, and that's what I get. Okay, now I happen to know that that is right. What's going on here? Does it pass the vertical line test? Well, it does. You might not quite be totally comfortable with that. You might want to zoom in a little bit. So I'm going to zoom in and come down to this section and zoom in and see what I get. Okay, you can see this is passing the vertical line test. Okay, so this is a function. Does it pass the horizontal line test? Certainly right here it does. Let's go zoom number 6 standard. Yeah, it looks like it. I could go out further. Now, I know analytically that this one definitely does pass both the horizontal and vertical line tests. So let's just go with that for now. But if you look at it and if you were to play around, you would be able to convince yourself that yes, it passes both vertical and horizontal line tests. And so therefore, it is 1 to 1. And so therefore, it does have an inverse. So now let's find that inverse. Now we have to be a little bit careful here. So we're going to start off by getting y equals f of x. And f of x is this part. So we have y equals the square root of x plus 2 minus 3. And we are going to switch the x and the y, or replace all the x's with y, replace all the y's if there's more than one with x's, and solve for y. Now, that includes any x's or y's related to the domain and range. Let's come back and have a quick look at this. What is the domain? Well, it's all x's greater than or equal to -2. So my domain here is that this is valid for x's greater than or equal to -2. I'm going to also replace this x with a y. This domain becomes my range. And, if you think about it, it should make sense. F is going from the domain to the range. F inverse picks up every range value and brings it back to the domain. So in other words, the domain of F is the range of F inverse. And the range of F is actually the domain of F inverse. So it makes sense that the domain and range switch, because F inverse is just taking the range and starting there and going back to the domain of F and ending up there. It really is, well, the inverse function. So this will also be replaced with a y. All right. So let's go ahead and do that. Let's do it in green. Why not? So I have x equals the square root of y plus 2 minus 3. Now, y is greater than or equal to negative 2. And I solve for y. I'll add 3 to both sides. I will square both sides. And I will subtract 2 on both sides. And then I'll switch the order. So I have y equals x plus 3 squared minus 2. Now, this is very interesting. This is a parabola. Remember, if you have f, whoa, that's crazy. If you have f and you find its inverse f inverse, the inverse of f inverse is f again. They're inverses of each other. But we just looked and said, hey, we had a parabola. It didn't have an inverse. And now we have a parabola and we're saying that it is an inverse? What's going on here? Well, what's going on is we have to be very careful with our domain and range. And this inverse is about to be restricted. We have that with our original function, the domain is x greater than or equal to negative 2. We also have that the range is y greater than or equal to negative 3. So we also have over here that y is greater than or equal to negative 3. For our new function then, the inverse, we have that x is greater than or equal to negative 3. All the way down here. Now, look at this parabola. Where is its vertex? Its vertex is at negative 3, negative 2. Why negative 3? Because we take the number that is subtracted from x. It's a negative 3 that is subtracted from x, so it's a negative 3 here, and we have a negative 2 here. This is the vertex. Our parabola is a concave up parabola because a is 1 with a vertex at negative 3, negative 2. So it looks something like this. It's always negative 2 or higher. So this makes sense. But additionally, we have a restriction that we can only keep this half of the parabola. This half here gets rejected. It gets thrown out. So with this restriction then, our inverse makes sense. So we have to be very, very careful, especially when you have square roots and squaring in particular, that you have your domain and you have your range for your f, and that you switch the x and the y, and then you pay attention to that because that new domain here could restrict the function you have. Okay, so altogether then, our original function is this one here, f of x equals root x plus 2 minus 3. So we have f of x equals root x minus 2 or plus 2? Plus 2. Plus 2 minus 3. And f inverse with, of course, the restriction that x has to be greater than or equal to negative 2 because you can't square root a negative. Okay. And the inverse function is x squared plus 3 minus 2, x plus 3 squared minus 2 with the restriction that x has to be greater than or equal to negative 3. With these restrictions in place, we're fine. and these truly are inverses of each other. Now, if you want, you could actually prove that to yourself by very carefully taking f of f inverse of x, figuring out what that is, taking f inverse of f of x, figuring out what that is. Be careful to make sure that all of the restrictions are satisfied, and you'll discover that each of those is x, and therefore those are inverses of each other. Okay, let's get into one last thing, the self-inverse function. So a self-inverse function is a function that is its own inverse. Now this sounds kind of paradoxical, but really it's not. All it's saying is, if you have some function that maps from a domain to a range, f, if when you take the outputs, each one, and apply f to them, it happens to take you right back to the input, f, then this f is called a self-inverse because the very function that goes back here is the same function that goes in the first direction. It doesn't mean that these outputs have to be identical to the inputs, right? 1 might map to 5. 2 might map to 15. 3 might map to 30. I don't know. But the trick is, whatever this function is, if it happens to be the case that f of 5 equals 1, and f of 15 equals 2, and f of 30 equals 3, then we have a self-inverse function, because f inverse is f itself. Okay? Now let me give you an example of this that is a non-trivial example. Oops. Okay, so let's take this. F of x equals x over x minus 1. This, I claim, is a self-inverse function. Well, how could we prove this? Two ways, really. My claim is that this is self-inverse. So I could say y equals x over x minus 1, switch them, solve, and see what is the inverse of this. And if the inverse of this turns out to be identical to this, then heck, it's a self-inverse. Okay, that's one way to do it. The other way I could do it is I'm saying, okay, I'm claiming this is a self-inverse. Well, then that means that f of the inverse of f, which is f of x, has to equal x. And also f inverse of f, which is f of x, also equals x. But these are the same thing, so I only have to show it once, right? So if f of f inverse of x is x, and f inverse of f of x is x, then f inverse is really the inverse. But what I'm claiming here is that the inverse is f itself. So if I can show that f of x is x, that also proves that we have a self-inverse. Let's do it both ways. I'll put this up here, save it for later. First, I'm going to do it the straightforward way. I'm going to say, okay, y equals x over x minus 1. Now I need to replace all x's with y's and all y's with x. This time, I have y in 2 spots. Some people get a little bit tripped up when they're trying to solve for y and y is in 2 spots. Don't let it bother you. What I'm going to do is I'm going to multiply both sides by y minus 1. Why? Well, because I'd like to get rid of this denominator first of all. So I multiply both sides by y minus 1. Then what I want to do is use the distributive property, x times y and x times 1. So I'm going to have xy minus x equals y. Now, any term with y, I need to bring it to one side so that I can get the y by itself. So I'm going to subtract y on both sides, and I'm going to add x on both sides. Okay, I did both of those things at the same time. finally, I will factor out this common y, like that. And how do we solve for y? Well, we divide both sides by x minus 1. Y equals x over x minus 1. So therefore, f inverse of x is x over x minus 1. Is that identical to the function itself? Yes, it is. So this is a self-inverse. I've shown that the inverse is itself. And we can see a quick example. Let's look at part of the domain and range. Let's say 2. What does 2 map to? Well, 2 over 2 minus 1, that's 2 over 1, that's 2. 2 maps to 2. Well, now going back the other way, what will 2 map to? Well, obviously to 2, right? If the inverse is the function itself, obviously 2 will go back to 2 again. Let's try another one, because it's not so trivial as just that. Let's take 5. Well, 5 over 5 minus 1, that's 5 over 4. 5 maps to 5 quarters. What does 5 quarters map to? Well, let's try it out. That's 5 quarters over 5 quarters minus 1. That's 5 quarters over 5 quarters minus 4 quarters. That's 5 quarters over 1 quarter. 5 quarters divided by 1 quarter. That's 5 quarters divided by 1 quarter like this, which is 5 quarters times 4 over 1, which is 5. So f of 5 quarters is, in fact, 5. It maps back to where it started. This isn't a proof that it's a self-inverse in pink. This is just an explanation, sort of an example, an illustration of what it means for a function to be a self-inverse, right? I'm just showing that f really is the inverse of itself. If you go from left to right using f, you can go from right to left using f as well. F equals f inverse. We proved it over here. Let's also prove it this way. Okay, so f of x. Well, f of x is the argument to f, and so everywhere we see an x, we're going to put our argument. Here and here, we'll put the argument, and the argument is the function itself. So this is going to be x over x minus 1. This here is f of x. That's going right in this spot here. And then I also need f of x in this spot here, down here. So I'll do it. I have x over x minus 1. And then a minus 1, like that. So f of x itself has been put everywhere that there's an x in f of x. This is f of x. Now, this is the same as x over x minus 1 over x minus 1 minus, well, 1 is the same as x minus 1 over x minus 1. Why am I choosing that? I'm choosing that because now my denominators match, and I'll be able to subtract these two fractions. So then my next step is that I have x over x minus 1 over x minus 1 over x minus 1. So here now I'm subtracting these numerators. That's what this is here. Okay, let's go ahead and do that. So we have x over x minus 1 over x minus x is 0 minus negative 1 is 1. And now a fraction of fractions, I prefer to think of it as a division of fractions. So I have x over x minus 1 divided by 1 over x minus 1, which is x over x minus 1 times x minus 1 over 1. I could reduce early here, divide one numerator by x minus 1, divide one denominator by x minus 1, and get x over 1, which is x. That's how I would prefer to do it. But just for clarity, I'll also do it this way. I'll actually multiply first and then reduce. X times x minus 1 is x onto x minus 1 over x minus 1 times 1 is x minus 1. Now I have a fraction with a common factor of x minus 1. So I'll divide the numerator by x minus 1, divide the denominator by x minus 1, and I'm left with x over 1, or x. And so we've showed it. We've showed that f of x equals x, which implies that f is a self-inverse function. And now we have enough for exercises 2I and 2J and Chapter 2 review, including the exam style questions. We've got all we need for Chapter 2.